Hello everyone, welcome back to another stat example. Today we're going to look at the exponential random variable. It's in our continuous family. It's one of the special types. In this problem here, we are looking at the amount of time someone spends inside Costco. So that is my random variable. And that's going to be my x. Now the problem tells me x is exponential. And what I remember is the parameter of the exponential random variable is the symbol lambda, which is the rate parameter. And what's unique is the problem, instead of giving me the rate, it gives me the mean. So I have to recall that the mean of an exponential is the reciprocal of the rate. So in a lot of these special random variable examples, you have to be aware of what the parameters are. For the exponential, we just need the one parameter, lambda. It's related to both the mean and the variance, and so we just want to make sure we note that. The other thing that can get tricky for exponentials is if you look at the units throughout this problem, we've got minutes, and then we have hours. So when I define my random variable, I want to make sure that I'm using the appropriate unit. And it doesn't really matter which unit, I just have to stay consistent. So what I want to try to find now is I'm going to work in hours because that's my question. So if I convert the mu, then I have here 40 minutes that's given, but that's also the same as saying, well, that's 2/3 of an hour. Okay, so this is the relationship that I'm going to draw between my lambda. So if I do it that way, I can go ahead and solve. I've got 1 over lambda is equivalent to 2/3. So that tells me my lambda is 1.5, 3 over 2, or 1.5. Okay, so that's the lambda we're going to use right here. And again, the units is in hours. So now I can go straight to the question. What's the question asking me? Well, it's asking me what's the probability that a person will spend more than 1 hour. So that's the probability that x is greater than 1. Now, I did not have to do this. I could have left everything in minutes, which would have meant that I would need to convert the 1 hour into 60 minutes. But I like the number 1. It's easy to work with, so let's do this. Now, for continuous random variables, unlike the discrete, I don't really have formulas I can plug into unless I'm doing it carefully. We have two options here. We can use the definition of integrals and integrate our little f, right? Our density function here. Or we could take advantage of knowing that the probability that x is greater than 1 is equivalent to 1 minus the probability that x is less than or equal to 1. Now, why do I want this? I want this because the less than or equal sign, this is nothing more than my Cdf value, which is the uppercase F. Now, I don't really want to do the integration, even though I can. I would instead use this Cdf value for exponentials that just looks like this. So now if I want to find probabilities, I can always use the Cdf formula. And this is, I just have to remember that the Cdf value gives me the area to the left. So to finish this example here, I will now plug in uppercase F of 1. And then recall uppercase F is the formula right above in yellow. I'm just going to move it down. And now I'm going to plug in my values. My lambda is 1.5. And the x value I'm shoving in is 1. So if I simplify, I've got 1 minus and then parentheses. The 1s will cancel out. I'm left with just e to the negative 1.5. Now, in some classes, you're allowed to leave it like that. That's simplified enough. Or if you feel like it, you can get a decimal equivalent. And if I work this out correctly, my decimal equivalent is 0.2231. And that's how we do probabilities of exponential random variables. For the second part here, we have the same distribution, but now the question is asking for the median time. So what is that? Let's draw out this distribution so we can get an idea of what it looks like here. So here's my x-axis, the time. Again, recall that you were given x is exponential, and the lambda, if we felt like dealing in hours, was equal to 1.5. Okay, and the note here is, again, we're dealing with hours and not minutes. All right, the exponential distribution looks like this. It's steadily decreasing. Let me draw that again on a thicker line. And what I'm trying to find is the median value. In other words, I'm trying to find some time here. And let me go ahead and call this little m for median, such that half of my distribution is to the left and half to the right. So that means the area here is 0.5. And similarly, the area here is 0.5. So the median is nothing more than just the 50th percentile, right? It's not necessarily the middle x value, but it's the x value within the distribution. So that's why we're drawing these areas here. Now, for me, the easiest way to do this is to work with the area to the left, because we already have a formula for area to the left. Remember, that was our capital F, which is this probability here, the area to the left. Now, we know for exponentials, it has this equation. So as long as I know the area to the left, I can shove it in here. And so what I know in this problem here is that I'm looking for the median. That means my area to the left is 0.5. And I'm trying to find this value m where that happens, right? So in this formula here, I'm just plugging all my parameters in, and this is the m that we're looking for. And if we were to change this up, if you wanted the third quartile, then you would change that 0.5 to 0.75 to represent 75% of my distribution being to the left, right? And you can work this with any percentile that the problem's asking, as long as you have the CDF equation, which we do for exponentials. Now I'm just going to go through some algebra. I'm going to subtract 1 from both sides. I get a negative half. Both sides are negative, so the negatives will cancel out, leaving me positive 0.5 equal e to the negative 1.5 times m. And then here, to get the m down, I'm going to do the inverse operation of exponents, in this case, the natural log. So natural log of 0.5 equals, and I'll go ahead and write all this out, natural log of e to the negative 1.5 to the m. And what this will do is my property of exponent allows me to take this exponent here and move it down. So in the next line, I've got natural log of a half equal to negative 1.5 times m times the natural log of e. But the natural log of e is just 1. So finally, plugging everything in my calculator, dividing both sides by negative 1.5, I get the median is 0.462 hours. And so again, the note is we're dealing with hours. If you want to deal with minutes, it was fine. You just would have to change the lambda in the beginning to minutes. And that's it.